Hello everyone, welcome to the introductory session of nuclear magnetic resonance spectroscopy, in short NMR spectroscopy. Myself Kamalesh Roy, Assistant Professor, Department of Biotechnology, Haldia Institute of Technology. If you are pursuing organic chemistry, biochemistry or structural biology, then you are quite aware of the fact that determining structure is a complex puzzle. So, and it needs a constant and extensive effort or studies, which is very much important for other issues like biochemistry and structural biology. But today we have a very elegant, non-destructive, and powerful tool for determining structure, which is nuclear magnetic resonance spectroscopy. In other cases, like if you look for in other cases, then you can see that in case of IR spectroscopy, it gives us the functional groups, whereas the knowledge about the functional group, whereas the mass spectroscopy gives us the knowledge about the molecular mass. In case of NMR spectroscopy, we can get an idea about the structure of the molecule, the environment of the molecule, as well as dynamics of any pathway of structural cases. So, let's talk about NMR spectroscopy, which is what is NMR spectroscopy? So, nuclear magnetic resonance spectroscopy, a powerful analytical technique for determining the three-dimensional structure and dynamics of molecules and atomic level. NMR is indispensable in biochemistry and biophysics, providing insight into the protein folding, ligand binding, and metabolic pathways. The technique relies on the interaction of nuclear spin with an external magnetic field. Now talk about what is NMR spectroscopy. NMR is already I have told you, non-destructive spectroscopic method that reveals the detailed information about the molecular structure. Key applications: structural biology, drug designing, metabolomics, and quality control in pharmaceuticals. Common NMR active nuclei: H1, C13, N15, P51. So what is nuclei? One, what is to be done with the nucleus? Let's talk about which are the molecules which are NMR active. Before we go into that, we have to understand how NMR works. What is the main principle of NMR? The fundamental principle is nuclear spin. Certain atomic nuclei possesses an intrinsic angular momentum called spin. This quantum property makes them behave like a tiny bar magnet. That means if there is a nucleus, then it must have some protons and neutrons in it, and rotation due to the rotation of the charged particles, there arises a angular momentum, and that angular momentum compels the nucleus to behave like a tiny bar magnet. When placed, and these tiny bar magnet, when placed in an external magnetic field, these spinning charged nuclei align with or against the magnetic field. That means in case of external magnetic field. So what are now the question is, what are the nucleus that produces a magnetic field? Now talking about the previous slide, that the nucleus is which is having only one proton, that means odd number of protons or odd mass number, which is not cancelled out by any other, then the nucleus behaves like a tiny bar magnet. For example, C12, since it is having 6 protons and 6 neutrons, so it will not be NMR active because it doesn't produces a small bar magnet. But C13, which is having 6 protons and 7 neutrons, so there will be a odd number, odd mass number, so it will produce a magnetic moment, as a result of which behaves like a bar magnet. Here also N15, P31, though N14 is also a nuclear NMR active nucleus. So H1, which is the most relevant because this is not radioactive, and without H we cannot think of any biomolecule anymore. So H is the most effective and important that NMR active molecule, a NMR active element or atom which is present almost all the biomolecules, we can say. So proton NMR or PNMR or HNMR is the most effective way for determining the structure of biomolecules. Here come to the resonance. Absorbs of radio frequency energy issues nuclear flip between spin states. The transition is detected as an NMR signal. Later on, we can understand what is actually. Understanding the nuclear spin. So let's understand what is nuclear spin. As I have told you, odd mass nucleus and even mass nucleus. What happens here? Odd mass nucleus, that is, has nuclear spin and a magnetic moment of NMR active. So let's talk about which are actually what is actually happening here in case of spin. Nucleus with odd atomic number or odd mass number, that I have told you, H1, which is having spin half because it is odd atomic number. C12, which is not having any spin, not producing any small magnet because it is 6 protons and 6 neutrons, so not observable. C13 is NMR active. Whereas N14, which is having a spin 1, not all nuclei are NMR active. The spin quantum number determines whether the nucleus can be observed by NMR spectroscopy. Now talking about nuclear spin, again I can give you a short idea about how nuclear spin is acting and behaving like a bar magnet. The nucleus with an odd atomic number, that talk about this one. The nucleus which is having a charge rotating in this direction and producing a magnetic field in this direction, like the arrows are going. Here we can see the nucleus is rotating in this direction and the arrows are moving in this direction, and that is what actually a bar magnet looks like. North pole and south pole and the magnetic field are giving aligning in this direction. So if the magnetic field are aligned in this direction, then we know from the knowledge of magnet that the north pole and south pole become in this way, and this is how a small bar magnet looks like. Now NMR, what happens in NMR? If we place the small bar magnet in a large magnetic field, then what happen? This is the small magnet, large bar magnet, which is having a north and south pole, and here we can place the small magnet like in this way. B0 is the magnetic field of the large bar magnet, and here what happens, there is a torque act on the small bar magnet, small tiny magnet, due to the large magnet. And here what happens, there is two options. That means the small tiny magnet can be aligned with the large magnet, or the small magnet can be against with the large magnet, like north to north, south to south. That is, the magnetic field direction, it will be same with the large magnet, what we call low energy, what we call aligned with the bar magnet. And if the small tiny bar magnet having the magnetic field just opposite to the large bar magnet, then we call this is the higher energy state and less stable. Let me tell you that this is the alpha state and this is the beta state, and don't think this is a small magnet. This is actually the nucleus, which are behaving like a small magnet. So the nucleus is placed in the large bar magnet. Now talk about alpha state and beta state. Energy level in a magnetic field when nucleus with a spin placed in the external magnetic field, as I have told you, B0, then adapt a specific orientation like alpha state, which is parallel to the state and which is a lower energy, as the picture representing that anti-parallel state, which is having opposite magnetic field to the large bar magnet, which is called beta state in the higher energy state. Now more nucleus occupy alpha state and there are some nucleus occupy anti-parallel state. That means the energy difference del E between these states proportional to the strength of the magnetic field, and the stronger the magnet produces larger energy gaps between spectral resolution. So now talk about now this slide will make you much more clear about the alpha and beta state. That means alignment and energy. Now this is alpha state where this is the direction of the B0, that is the large magnet, and this is the direction of the small tiny magnet, which is aligned, which is called alpha state, which is the lower energy state, and which is against the magnetic large bar magnetic field, which is called beta state. This is a nucleus, this is another nucleus. So alpha state to beta state, there will be an energy difference which is del E, and that is the h nu amount of energy which is needed to be supplied. That means the frequency needed to be supplied to flip. The phenomena is called flipping from alpha state to beta state. The magnetic field of the spinning nuclei will align with the external field and against the field. The photon with the right amount of energy can be absorbed and cause the spinning proton to flip. Now, resonance and energy. The resonance condition. That means when radio frequency radiation matches the energy difference between spin states, nuclei absorb energy to flip, and del E equals to h nu, that is gamma h cross b0, where gamma is the gyromagnetic ratio, that means nucleus specific. Which nucleus we are working with, gamma depends on that. B0 is the magnetic field, and h cross, as we know, that is h by 2 pi, from the lower energy state to higher energy state, and that is the equation that we can have, and depending on which we apply energy. So that is chemical environment shielding. Now talking about, if all the protons absorb the same amount of energy to flip, then how will we understand, how will we distinguish the different protons in the field? So what happens here, that is called chemical environment. That is, all the protons, that means all the hydrogens that we are talking about, will not have the same environment in a molecule. So not all protons experience same effective magnetic field. Electrons surrounding the nucleus create their own small magnetic field and opposes the external field, phenomena called magnetic shielding. So what is shielding? Let's talk about shielding. High electron density around the earth, that let's talk about a little more higher, little more previously what we have learned, that is an atom which is having a nucleus is surrounded by the electrons, that is electron cloud. So nucleus is actually shielded by these electron clouds. But if this atom is attached with any electronegative atom, then the electron cloud, what happens here, then this electron cloud will actually be pulled by another atom, and the nucleus will be exposed, and that is what we call deshielded. That means if the hydrogen atom attached with which element matters, because if this element is much more electronegative, then it will pull the electron cloud towards itself, as a result of which the nucleus will become exposed towards the external magnetic field. But if it is not that much electronegative, then the electron cloud will be surrounded to the nucleus and it will be shielded. So we need a higher amount of energy to flip the proton or flip the nucleus of hydrogen. So that is totally depend on the environment, the hydrogen atom attached with which atom. That means the uh, total environment of that hydrogen atom, that means representing the total molecule itself. So I hope you have I have made you understood what is shielding and deshielding. Let's talk about this slide. It will make you much more clear about that. Actually, a nucleus, which is naked nucleus of hydrogen atom, absorbs 60 megahertz energy and 14,092 Gauss, and that makes a proton to flip nucleus. But actually that never happens, because we don't get a naked nucleus in case of any molecules. So the nucleus is surrounded by the blue color electrons. Here we can show the blue color in this way, that is blue color electron clouds which are shielded. So if you apply a certain amount of energy, then this energy will be somehow uh, cancel out by the electronic, that means the electron cloud. And if you apply this, then in case of nucleus it will reach in 14,092.7, it is calculated in case of proton, in case of hydrogen. But you need 14,092, but it has reached to the nucleus 14,091.7, so it will not flip the proton. So what you have to do, you have to increase your magnetic strength from 14,092 to 14,092.3 Gauss. But 14,092 was the specified magnetic field which is required to flip the proton. But if you increase this zero point 0.3 Gauss, then in case of nucleus it will reach 14,092, because the the electron cloud will destroy some of the field, as a result of which the ultimate effective field will be 14,092 at 60 megahertz, which will reach to the nucleus and flip the proton. So this difference and that increasing will differ in proton to proton. So let's talk about proton in a molecule. Depending on their chemical environment, proton in a molecule are shielded by the different amounts. Like this, you can say this methyl alcohol molecule, there are two kinds of hydrogen. These three hydrogens are attached with carbon, which is less electronegative, but this hydrogen is attached with directly with the oxygen, which is more electronegative. So this hydrogen is less shielded and these hydrogens are more shielded. So less shielded hydrogens will be more naked towards the external magnetic field, and more shielded hydrogens are much more shielded towards the external magnetic field. So from previous study we can understand these hydrogen needs least amount of magnetic field, but this hydrogen needs more amount of magnetic field. So two kinds of hydrogen we have got, and we will get two peak for that. So let's talk about NMR peak. Number of signals shows how many different kinds of protons are present. That means if we have in previous cases we will get two peaks, because there are two kinds of hydrogen. Location of the signal shows how shielded or deshielded protons it is, because this is much more shielded proton, and if you move left hand side you will get the deshielded protons, and this peak is higher than that of deshielded peak, because this category of peak contains three hydrogens, but this category of peak contains only one hydrogen. That means intensity of the signal shows the number of protons present in that region. That means this under this peak we have three hydrogens, so this peak is much more higher. This peak is much more in right hand side because it is shielded hydrogens. This peak is much more left hand side because it is deshielded hydrogen. This peak is smaller because it contains only one hydrogen. Splitting we will understand in the next lecture. Now talk about this is the actual NMR diagram looks like. And now talking about tetramethylsilane. That means here we can see the graph from left and right I am saying, but which respect left and right is happening. The respect is TMS, that means tetramethylsilane, which is having hydrogens most shielded, because it is attached with the silicon like electropositive atom, as a result of which hydrogens are mostly shielded, no deshielding happens. So this will placed in the most right hand side of the graph. With respect to TMS we get our peaks of our molecule. That means TMS is a molecule which is a standard and which is to be mixed with all the samples. TMS is added to the sample. Since silicons is less electronegative in the carbon, organic protons absorbed in the downfield. Now talk about more about a chemical shift. Chemical shift, which is measured in delta ppm, shift downfield from the TMS spectrometer frequency. Suppose you have got a frequency at suppose you have got a peak at 360 hertz here, and your machine has a frequency like uh, 600 megahertz. Then according to this equation, downfield 360 by 60, you will get 6 delta ppm. So the peak is appearing at 6 delta ppm, and 0 is taken as a TMS measured in the parts per million. So here what happens is why ppm? Using ppm, now let's understand why we are using ppm. Using ppm makes chemical shift independent to the spectrometer magnetic field strength, allowing universal comparison of data across different instruments like sample minus reference by spectrometer into 10 to the power 6, and then we can get the actually normalized delta which is internationally accepted. So typical values of chemical shift, like we can see that in case of this B0, that is introduced magnetic field, and B0 this is induced magnetic field, and this is what happens in case of benzene. This is what happened in case of ethylene. This is what happened in case of uh, the nucleus behaving like a tiny bar, it magnet, and this is what happened in case of ketone group. So different uh, chemical shift is found will have different values. In next lecture we will understand about the splitting of the peaks. That means the much more detail on the peak. And thank you for now. I hope you enjoyed the lecture. Thank you.